Okay. Well, thank you so much to the organizer and the CMS for putting together this event and inviting me to speak here. So I mostly hope to be learning here from all the exciting things that David and others have been doing. But I'll start today by introducing some of the superficial parts of the story that I think we're all trying to tell. Because that's the only part I understand. But I'll start with this rather old analogy between knots and primes. That's due to, I mostly learned it from a paper of Barry Mazur, but I think it's also attributed to a number of other people. So I'm not sure exactly how the history of this subject goes at all. But nonetheless, I'll start with this very dry looking slide of notation. Mostly I put this together to keep myself disciplined because I find it very hard to use notation consistently. So I just put this at the beginning to train myself to be a bit organized. So I'll try to consistently use F for an algebraic number field. And oftentimes they'll be totally imaginary to avoid some cohomological complications. And O of F there is the ring of algebraic integers inside F. And I'll denote by X its spectrum. So then there's a bunch of other stuff. FV will be the completion at some prime. Also, we view it as a point of X. XV will be the spectrum of this ring of integers of this completion. I'll denote by KB the residue field. So I denoted by V this point, maybe this, okay, never mind. So, but V also, I'll use the same notation for the spectrum of the residue field. So which therefore comes with an inclusion into the scheme X. Then by T of V will be the spectrum of the completion. So that's X of V, this completed spectrum minus the point V itself. And then B will be some finite set of points. And X superscript B, you'll just remove those points from X. And T subscript B is just the disjoint union of those spectrum of the local fields. Then there are a bunch of fundamental groups. So this is all the notation. Sorry about this very dry slides, but we can return to it later if anything is confusing during the rest of the exposition. So these groups in particular are so-called étale fundamental groups, which sometimes can be thought of as Galois groups. These two can be thought of as Galois groups. So usually this is the Galois group of some restricted ramification field. And this is the Galois group of a local field. Sorry, this is also the Galois group of what's usually called the maximum ramified extension. So these are easy to write down notations for, but very, very mysterious. I mean, this one is not mysterious, but these two are very difficult for number theorists to understand even after centuries of study. We really don't have a good grasp of what these groups are like, in spite of a lot of effort. But nonetheless, we can write down some symbols for them and start to study them. Again and again, we restart many times, and I've restarted even in the course of my research. Okay, so that's just a notation. Now I'll remind you of this stopped functioning again. Now what's happening? This works anyways. Okay, I'll just stop bothering with this. So here are the analogies. The spectrum of these the ring of integers of the algebraic number field is supposed to be analogous to a three manifold. And I'll review next time some rationale for this, the most important being some cohomological dimension of three that underlies this analogy. And then knots and primes come into this picture because that spectrum of the finite field of some residue field of O of F included inside X is supposed to be like a knot inside a three manifold. Now, there are many reasons for thinking something like that, and I'll come to a very good reason, I think, towards the end of this lecture. But the old reason was that if you look at the fundamental group of V, So that's the Galois group of a finite field. So that's Z hat. That's a topologically cyclic group. So for many purposes, cohomological purposes, this spectrum behaves like a K pi 1, where pi is just Z hat. So it is very much like an S1 included inside the three manifold. So that was the source of this. If you look at the spectrum of the completion at V of OF, so this is a fairly standard thing in algebraic geometry, that you take a subscheme of a scheme and you complete around there, that you're viewing that as a formal algebraic analog of a tubular neighborhood. So that's an old idea. And so that's what we're employing here. So if we think about V as being like a knot inside the three manifold, then this completion, if it's a tubular neighborhood, should be like a solid torus. But if we just remove the knot in the middle from that solid torus, then we get something that's like the boundary of that solid torus, named hollow torus. If you want to make the analogy more compelling, you can think of the knot as actually having some thickness. They're moving actual chunk around the knot. Torus also, rather than our idealized one, it can be an actual. It's a perfectly sensible statement. Now, B was supposed to denote the finite set of points of X. So that's like a collection of knots inside. There was a link inside the three manifold. And when you remove those finite set of points, again, you can think of yourself as removing a little closed tubular neighborhood around that knot, in which case you get a three manifold with boundaries. So this deleted ring of integers, so finite set of primes removed, that's like a three manifold boundary. And this TB, the disjoint union of these analogs of tori, is just a boundary of XV. Okay, so that's the basic analogy. So X is a three manifold. XB superscript B is a manifold with boundary. T sub B is the boundary. That's the main analogy that it's referred to as, oh, sorry, and this second line, V included inside X as being like, not, that's the analogy. Any questions up to here? I know I said confusing, so we'll try to elaborate. But you can ask some questions. Right. So in fact, the goal of my lectures, or maybe all these analogies from the viewpoint of topological quantum fields, where these analogies become better schematic dimension. I feel like even with understanding I have the TQFT viewpoint aspects of this analogy in a way that it leads to, I thought, but I knew anyways before thinking about it in this way. Right. Some people say the number theorists use this word analogy too much. More before we return. There's an older analogy to many people again, but by Andre Weil, written to his base, or is it? Right. So this has two. One is this old. It's folklore. So what's that? If you take this algebra, then this is very similar curve over a finite G between function field. This is in different ways, including algebraic reasons and topological reasons. And if we take the spectrum of integers x itself, it is somehow analogous to the curve C, right? And similarly, if you remove an element. So I write something like this, we're allowing the possibility that B is empty and S is empty as well. So all those analogies are being notated together in one line. Yeah, I didn't review these slides before the lecture, so I'm not completely sure what comes after what. So, but anyways, when he writes about this analogy, he makes this following remark: that between this analogy between number fields and function fields is so strict and obvious that the or a result in arithmetic is almost word for word. It's probably not the same, right? But the difference from function field to number field, that much very, very, very did it. I don't know, odd with this. That's something. So, whole element. Those maybe, right? That and that David is an expert on. The, that is inspired by correspondence for number fields, of course, but then it developed into a lot of interesting things in its own right, some of which we'll talk about this week. But there are other consequences. So, for example, Go's proof of the fundamental lemma, I think it also should be viewed as coming out of this analogy, since after all, he proves various statements over function fields, out of which originally through some convoluted argument, including mathematical logic, you get fundamental lemma as Langlands had formulated over number fields. Then things like Peter Schultz's proof of the weight monodromy conjecture for complete intersection varieties. This also takes a result in function fields and translates it over somehow to completion. Sorry? Sorry? This is Schultz's famous theorem. I hope I'm not formulating this incorrectly. This was the first application of perfected field. In those of hyperphysics, reduce the book. Never mind. Sure. I don't think I often make these mistakes. I think this is correct. Anyways. Right. So that analogy is good and dandy, right? But Wei, in the same letter, as I said, he sort of extends this to a trichotomy, meaning there are three parallel texts, right, that are supposed to be related to each other. So in other words, he says pretty much this, that as you go from a number field to a function field over a finite field, it should be viewed as just an intermediate point in a bridge linking the number field and the field of meromorphic functions on a compact Riemann surface. So you actually have this trichotomy and various properties of these three objects that form a parallel text. Now, this is also interesting, and many people, algebraic geometrists, only know about this. But here, he does express the analogy more cautiously. Okay. So this twiddle here, as we said, is very good in many sense. The second one, he says, it's okay, but distance is not so large that a patient study would not teach us the art of passing from one to the other and to profit in the study of the first from knowledge acquired about the second. So in other words, they're kind of useful as providing insight for each other, but maybe to say that this is really a strict analogy. And so the thing is, now we have, I think, a pretty good understanding of this cautiousness over here. And that's a large part of what we'll discuss this week. So for one thing, of course, we know some very obvious and superficial ways in which this analogy is not right. And so the superficial reason is that the better analogy is you should not look at the field of functions on C, but the field of rational functions on C bar, the base change of the curve to the algebraic closure. So there you get something much closer to a Riemann surface, and its field of functions is much more like the meromorphic surface. So this is better essentially for reasons of dimension. So in other words, if you compare C and sigma, their dimensions, the cohomological dimensions don't match up. C has dimension 3, whereas sigma has dimension 2. That's the main difference. So in fact, if you go to the algebraic closure, this gets fixed. So that's one kind of superficial remark. But you see, so then we can ask, we actually have two separate analogies, one between the field of algebraic functions on C bar and the meromorphic functions on the Riemann surface on the one hand, and the other, there's an analogy between number fields. So you could ask, now can we fix the trichotomy by sticking other things, one here and one here, right? So that's the question. What I'm going to do here is, for now, we'll focus mostly on the second side, although there's a lot of interesting work with completing this dichotomy as well. And the way to fix that is reasonably easy. So as we said, C bar, the curve over the algebraic closure of a finite field, is similar to a Riemann surface. So we view it in this way. The C bar we view generic fiber of C, view it together with its map to the spectrum of the finite field as being fibered over S1. So this is the kind of topological way of thinking about over the finite field itself. So here, remember, we already said the spectrum of a finite field is like S1. So C is fibering over it. So this is just like a point or something contractible, mapping to S1. Here we have a fiber, and this thing is supposed to be like. So we see that C itself, well, I already said it, I'm just putting it on the slide, is analogous to a fibered Riemann fibered over S1, with fiber at a base point, let's say, being Riemann surface sigma. So this is the better analogy, what they had originally thought in the dichotomy letter. It's kind of interesting because in a way, this one is probably somewhat obvious to everybody now, but because even though Wei is the originator of this idea of arithmetic homologies in some way, this homological dimension, difference of homological dimension was non-obvious at right? So somehow the fact that KC itself is not quite like a Riemann surface, or C itself is not quite like a Riemann. Still at that point. And of course, this is compatible with the analogy before between the spectrum of the ring of inserts and the curve, right? Over a thing. So this diagram, and from the point of view of TK, presented in ad hoc manner, right? Let me just mention and just full of, but that's okay because that and that's not transmitting from. All right. Amateur's review of TK. you have a field theory of dimension D, manifold of dimension D, a model for space-time. Then you have typically a fiber bundle over M. For example, the important case is just a product bundle. There might be tensor bundles, principal bundles, bundles of connections on a principal bundle, or it could also be a stack. And with nowadays, people do so many things. People around 30. About the theory, you have to give a function on the space of fields. That's usually called an action. Again, this idea is also being modified in ways that I don't understand, but this is good enough, again, for our purposes. A theory is given by a function that's typically expressed as a local function of the fields integrated over the manifold. So this is the way field theories are usually specified, by giving such a function. And then in classical field theory, you look at the extrema of that function, satisfied, defined by some Euler-Lagrange equations for that action. And somehow, how does this behave? What's the structure of this? Is supposed to tell us how the fields evolve in time and things like that. Again, the reason I'm going into this kind of thing is so that people will correct me afterwards. So please speak up if I'm misleading other people as well as myself. A very superficial way of saying what one does in quantum field theory, right, is that instead of the Euler-Lagrange equation, you look at integrals like this. So somehow, I mean, I'm being very casual about the constants. There might be some I over H bar and things like this in actual quantum field theory, but I'll ignore all that and just say that there's some exponential measure, right, involving the action with respect to which you integrate the field over the space of. Yes, that's right. Yeah. It's not a fundamental group. Is that the question? Yeah. That's right. Yeah. That's right. That's right. There's some kind of a pedagogical controversy whether it's actually 3.14 or not, right? And anyways, right. So we will encounter things like this actually in my lectures, even though I don't quite understand this. And of course, in some sense, maybe nobody understands it, but people work with it in various ways. But I will write down analogs of these expressions later on. Like just as part of the reason I'm mentioning this elementary stuff, which most people here understand far better than I do. And integrals like this, well, these are often viewed as invariants of the manifold. Once of the theory is fixed, you get it to make sense. Actually, maybe I'll skip this slide, move over to started a bit late. Right. So another thing you can do with this field theory is if you take a manifold with one lower dimension, right, and consider the theory on a product manifold like X cross an N cross an interval, so there you can formulate a vector space of initial conditions with the Euler-Lagrange equation on N, and this vector space. So in other words, you can associate to this lower dimensional space of a vector space. This is this I wrote down because this is a way that I like to think about it, which makes it somewhat easier to conceptualize a lot of the things that go on. But you don't have to take it seriously. But roughly speaking, they should be sort of as functions, holomorphic on the space of initial conditions. Yeah. There are other kinds of constraints that you can put on the space of functions in order to formulate vector spaces. And there's this idea that if you have a cobordism that connects one D minus one manifold or code, you could get an operator, a linear transition on one to final condition. One way of thinking about it is involving these horrible patterns, then use that to move that as a kernel at the end, and then integrate linear transformation from functions on one to function. So I don't know at which point I have to start. Maybe this is a reasonable point. I don't know. Yeah. Anyways, in topological quantum fields, there's this monoidal property where the empty set, for example, gets assigned the C vector space C, and disjoint unions go to tensor product. And if you change the orientation, I forgot to mention the orientation from the beginning. I should have said oriented manifold. It goes to the dual vector space. So there are various justifications because disjoint go to product. That's the basic. And you together with this business operator associated to cobordism trading of vector space associated. This is a nice transformation property. I'm not sure why I put this cycled slides from a book. You can see what the idea is. And so it's like something that goes from the back to the manifold. So this is I get a little bit more this. The other way of thinking about it, which seems to be very important, is somehow only in reading your paper, actually, I sort of realized how important this is, right? So it's another way of thinking about, well, unless I misunderstood, you should correct me at any point, right? Another way of thinking about this vector that you've associated to the manifold with boundary, right, is that if you think about the function, the solution space on the manifold M, and you restrict that to the space of fields, classical fields on N, right? Then that actually, typically, this has the structure of a symplectic manifold, and this will be a Lagrangian submanifold. The space of solutions to the field equations. Yeah, that's what M is, and Sn is the space of initial conditions. Right. So that's typically a Lagrangian submanifold inside the simplexing manifold. And there's this general mantra, and I don't know how well it actually works, but that somehow when you quantize this kind of picture, right, this will go to this vector space, this Hilbert space of the theory, right? But then that Lagrangian submanifold gives you a vector inside that Hilbert space. So this works very well when you have quantized a symplectic vector space or something like that. In general, I think you encounter all kinds of difficulties in trying to make this actually work. But in topological theories, I guess you can make it work much better than general quantum field theory. And for example, in the case of when you're quantizing a symplectic vector space, each Lagrangian will come with a collection of annihilation operators, and you look at the vector inside the vector inside the quantization of the symplectic vector space annihilated by those vectors, right? And then you get a line, and up to a scalar, you get a vector. So that's the general idea behind this construction. I think for actual quantum field theory, that's not topological. It's hard to make work, but the general principle carries over, so that in TQFTs, you can often do this. Now, so here's where I'll say a bunch of things that I don't quite understand, that I'm trying to understand from David's paper, is that now so far I've talked about kind of this Atiyah-Segal type of quantum field theory, where you just associate a number to something of top dimension and a vector space to something of codimension 1. But then in this extended field theory, you get a structure that you associate to all the lower dimensional manifold, right? Codimension 2, codimension 3, and so on. And the general idea is that, for example, to codimension 2, you're supposed to get a 1 category. Codimension 3, you're supposed to get a 2 category, and so forth, right? But one perspective for getting these categories is that you can think of them as the quantization of K-1 shifted symplectic structure. That is, when you look at the fields that live on a submanifold of dimension n, codimension k, right? And you cross that with r to the d minus k or an interval or something like that, and you consider something like the initial conditions in codimension k, what you end up with naturally is a K-1 shifted structure, and its quantization naturally. Another way of thinking about this process. I don't know who this is due to. I learned all of it from Pavel Safronov, and he gave me a bunch of references. So I'm not going to be able to even be mildly correct about the attribution. But I'll mention this anyway because it seems to be very important in your paper. I'd like to understand this better. Again, correct it if I'm saying something wrong here. So in this picture, right, you have one manifold with one higher dimension whose boundary is of dimension k. Okay? Then again, the fields on that bulk manifold has a Lagrangian structure inside this so-called shifted symplectic manifold living in codimension k. Okay? And that gives you an object here. Similar, by a principle similar to what happened with the vector space and a vector in there. So this is the general principle that one has to somehow understand in order to understand their approach to the Langlands correspondence, right? So, for example, remember when k is 1, this is just a vector space, and this is just a vector, right? When k is 2, in the codimension 2 case, this will be a category, and this will be an object in that category, right? And what's very nice from this point of view is that all these extra higher structures supposed to just come from quantizing these classical fields and maps between them. And that seems to be a very idea that I hadn't quite appreciated properly by these papers. So this is what I just said, right? Uh, Paper of David and Akshay and Yanis. And especially, it's important to understand the case when k equals 2, so that you get a category and an object like that associated to a Lagrangian. Coming up with suitable Lagrangians that will do this is a large part of the classical theory developed in. Sure, no. Oh, yeah, sorry. I should have said again. I don't really know that. I have not. It's not that I don't really know. I have no idea of the history of the subject. Nonetheless, what I meant was its applicability to the Langlands correspondence I learned from your paper. Right. So, first, the important case is that of a boundary condition. Right? The boundary condition gives you such a Lagrangian, right? Thereby you get an object inside the category associated to something. So category might be a category of sheaves. Well, I guess you'll say more about this later. A category of sheaves of the sort that you see in the Langlands correspondence, and then a boundary condition will give you an object. Maybe a few other things I'll say about is again very well known to most people here. I think if a dipole M is glued to those two pieces, right? Uh, the object, well, that you is obtained vector space of boundary by in a vector. A very important variant is product and interval mapping cylinder from the number that you get, or and there are higher categories to become mind-boggling. I'm trying to. Okay. About the first intellect is dichotomy. Okay. It's from so I present at least today one amusing things before going into the generality. So suppose there were multiple field theory that you could apply to these arithmetic objects, right? So what I'm about to speak about, in fact, is a 3D transformation. That's what underlies this discussion, that I'm going to introduce it in a kind of ad hoc way. And I think it will be, I hope the experts will agree that the structures are those of 3D transformation theory. But anyways, let's look at Weis trichotomy, or our correction of Weis trichotomy from this point of view. So remember, what it should do is it should take the curve over the finite field and associate with a number, right? On the other hand, to C bar, because that's a two-dimensional object, you should associate a vector space, right? So that's the way this is supposed to work. Because it's a three-dimensional. In the four-dimensional theory that those guys have in mind, you'd get instead an object, a category here. Right? Now, but remember the analogy was that this curve over the finite field was supposed to be like a mapping center, actually. Is that supposed to be like a fibered manifold? Sorry, I get a fiber tree manifold, where the fiber tree manifold, of course, can also be thought of as a mapping cylinder obtained from a monodromy diffeomorphism as you go around the circle, right? What is the circle? What is the monodromy diffeomorphism in the case of arithmetic? Oh, sorry. At first, as I said, I forgot what order I put these things in. The gluing formula that we discussed a moment ago says that, in fact, the isotopic classes of F should act on the vector space associated to sigma, and the number you get for the mapping cylinder should be just a trace acting on that vector space, right? But what happens in the number field case is that this curve is supposed to be like the mapping cylinder of C bar, the algebraic curve over the algebraic closure, where the monodromy diffeomorphism, the role is played by the Frobenius action. So that's what we should get. And this actually works in some sense, right? I mean, there are many ways to make it work. So here's a construction that worked out with Akshay a few years ago, and then forgot about it because I'm too lazy, and Akshay is busy thinking about far more important things. So it just laid there, but it's kind of interesting as a motivating construction of these arithmetic QRT ideas. So what we can do is we can take that curve C bar and lift it to characteristic 0. So what this here is, so K bar is algebraically closed field, algebraic closure of a finite field, and you take his width vectors. So this is like the maximum unramified extension of ZP, that kind of object. Huh? So every curve can be lifted to characteristic zero in this way. I forgot the notation. JY is the Jacobian of Y. Sorry, I left out one bit of notation. And you choose a suitable theta line bundle, right? And J of Y. So giving a principal polarization of Y. Now Q, remember, was the cardinality of K. So we're also going to choose an odd prime. Sorry, I should have used a prime-like notation, but I didn't. I just called it N, right? Odd prime that such that NQ is congruent to one mod N. Right? What this means, of course, is that FQ should contain the nth roots of unity. Look. So what we're going to do in a very ad hoc way is associate the vector space to C bar, which is just the global sections with the Jacobian, right, of L to the N, and then just tensor that with C. So you'll see, again, this is very much like Hilbert space associated to Chern-Simons theory of level N, I guess, right? Or 1 over N, whichever it is, right? But here's a kind of amusing fact. This thing here is acted on by a finite Heisenberg group with center given by the roots of unity and roots of unity. I'm just writing down the group law of the Heisenberg group. But it's a general fact that that space of global sections of L to the N is Heisenberg group. No fact. Right. But there's also an symplectic group intrusion of the Jacobian. Intrusion of the Jacobian is a symplectic vector wave pairing. And but in fact, the symplectic on which the Heisenberg, I don't know if I wrote this somewhere, the representation of the Heisenberg. And is that the symplectic group. That's right, but in just the symplectic kind of anomaly disappears. I'll say a little bit about what happens is C is defined over FQ. Yes, X n torsion of the Jacobian, because the n torsion of the Jacobian, this is over, say, this characteristic zero lifting, this field, the bit vectors of K bar, but this reduction mod, the maximal idea is actually an isomorphism on the n torsion. So the Frobenius actually acts on it. And it acts by symplectic transformations. So the reason for that is because of that condition that I wrote down a moment ago. That what was it? Which was it? Q is congruent to one mod n, right? Because so in general, when you act when you apply the wave pairing, the symplectic pairing, apply Frobenius first, then it will go through the Frobenius action on the result of the pairing. Okay? We just define number. You need this assumption, but somehow I never focused enough to get rid of it. You should assume that there's a Lagrangian subspace inside the symplectic vector space that is stabilized by the Frobenius. And that trace a moment ago is just up to sign is the square root of the n part of the class number of C. So this is kind of a funny trace formula. Again, it's relatively easy. It's a new sort of trace formula where you get square roots of class number. So don't arise too easily in number theory. So the point is that by applying EQFT to the correction of phase trichotomy, you get an interesting trace formula involving an arithmetic invariant. So in other words, the Chern-Simons style invariant, what I'm claiming to be the Chern-Simons invariant, is just square root of a class number. So as I said, there's a kind of four-dimensional theory of these guys, corresponding to this story, right? Where instead of a number, you'll get a function and things like that, right? And so, but this is the three-dimensional theory, and I'm claiming there's kind of a Chern-Simons theory. My student Yan Yao Chang is actually analyzing this formula from the point of view of Chern-Simons theory itself, in a form that I'll describe later, mostly in the arithmetic case. Maybe I'll give a sorry. I'll tell you later. Yeah, for the moment, it's slightly ad hoc. So this looks like the Hilbert space associated to Chern-Simons theory, taking the global sections of the set atom power of the set alignment on the joke. That's all I'm saying at the moment. And now we have the symplectic transformation, and it's the monodromy transformation. We're taking its trace, and so that's that should be the Chern-Simons invariant for C, abelian Chern-Simons invariant for C. So that's all I'm saying so far. Maybe I'll give a quick proof of this formula because it's somewhat amusing. As I said, this vector space of global sections is the unique irreducible representation of the Heisenberg group with trivial central character. So you can also realize it, right, as the functions and the Jacobian modulo this Lagrangian subspace. So that's another realization of the same representation, right? So that's now I think yeah. Well, you actually maybe I'll skip this proof because you do have to set up some notation for it, and maybe it's a little bit of a bother right now. Okay, let me skip this proof. We can return to it later. It's interesting. Yeah, this is where I should have reviewed the slide. It's relatively easy once you have this setup of well, this proof that the symplectic this confinement representation actually yields that proof of that relatively easy one. Right. So I guess what I'll do instead of giving you the proof of the formula is I'm going to tell you the plan of what I plan to do for the remaining lectures, as well as I think is a plan of what I hope to get from their lectures. So, I'm going to, I guess it's sort of to help me get this done. So remember, this is just review analogy and notation from the first two slides. Arithmetic three manifold T XB is the three manifold of various things, right? That we introduced. So some aspect correct it, but in fact it can also be improved, right? But for example, if we look at sheaves on these objects, right? Their analogy between them is actually much better than the geometric objects themselves. So we'll be looking at various sheaves on these spaces, right? And of course, once you start looking at spaces, sheaves, this is not so different from spacetime. So many analogies focusing on sheaves. So for example, it is simply of these represent the fundamental group of X, homomorphisms to some p-adic lead. In other words, the moduli space, right? Or for some sheaf of p-adic kind of moduli spaces are very important. I should say it might be a finite growth of typical picture you should, or the p-adic points of. So these are the kind of moduli spaces. It's very natural to see these as the fields in the sense of physicists, right? And try this to the central object in number theory. Look at this to us. For example, right? Suppose you take one of these primes inside X, right? And also fix a representation of R, or you should, of course, a finite. If you do that, it's a represent, right? Why? You can take any representation here, right? And even Frobenius conjugacy class, then take the trace on the finite dimensional group. So this way you get a function on moduli space associated to a decorated prime with a vector space attached to it. So this, of course, physicists know very well as a Wilson loop function. And what I'm claiming is not between these kind of decorated subsystems and much better than observable. Like, I it's also very well known in number theory, right? We just didn't think of it previously as like a Wilson loop. And I guess we didn't necessarily think of it as being like a function on the moduli space necessarily. Thinking of it, the representation as a variable isn't such an active thing that number theorists did. But of course, there will also be actions and path integrals, right? Or at least baby versions of that, right? Because you see, this is kind of a local thing concentrated on a subscheme, but actions are global functions of fields, right? And then we also want to do path integrals. So what I'm going to do is in the next lectures, describe an arithmetic Chern-Simons theory of a rather simple-minded sort. So what does this consist of? Well, we'll take a space. Well, you can do more general things than that, but to keep things concrete, you can take one of these spaces of representations of the fundamental group, right? And then define a Chern-Simons style function on them. So we'll do this directly. In other words, you can think about the arithmetic field series again purely in terms of analogies. You get vector spaces, numbers, etc. Right? But in fact, I'll try to show you how, at least in a simple situation, you can actually write down a function on moduli spaces and also do path integrals. And also on these boundaries, right? Boundary moduli spaces associated to this manifold, arithmetic three manifold with boundary, we can define a line bundle and the vector space of sections of the line bundle. So this, and then with the manifold with boundary, we'll associate a vector inside the vector space. In other words, this kind of sort of superficial analogs of the topological picture work fairly well in this situation. It's not, one doesn't have to be conjectural, yet structures of this. So when I was thinking about these things years ago, in this I was primarily thinking about some way of studying L functions using this half-baked ideas. And a referee wrote a scathing report pointing out that these are very half-baked. These ideas are very half-baked. And let's say, as I said, I thought in this old paper that these constructions should be related to L functions because L functions can also be sections of determinant lines, the basic analogy that I studied about, non-equal trivialization of determinant line bundles on suitable computations. And somehow physicists seem to be good at constructing. But this wasn't good enough because, of course, yeah, in this three-dimensional approach, you end up with a line bundle over local moduli spaces rather than a global one, right? Instead, what you should have is something like a line bundle over the global moduli space, right? And a section of that line bundle, right? That should be much more the flavor of an L function should be like, right? But I couldn't even conceive of such a thing because it seemed like, of course, I was thinking about very naive aspects of TQFT, which I still am. That's where I'm stuck still. But nonetheless, getting such a thing seemed to require something like an arithmetic four manifold. And you have to be much more speculative than I already have been. Imagine that there is such a thing, right? But then David and Yanis and Akshay pointed out that in fact, you don't need an arithmetic sub-3 manifold. You just need boundary. Space of boundary conditions is enough to detect. So in fact, slightly more generally, wherever the Lagrangian comes from, if you have a Lagrangian structure on suitable moduli spaces. So from the point of view of getting Lagrangians inside spaces of fields, there's no difference between having manifold, having boundary conditions. So this is the kind of thing that I didn't appreciate at all before I was drummed into me by this 450-page paper. So this the next part is even more is real speculation. Yeah? Um, but as I said, this is what I sort of like to get from your lectures and try to understand better.